Hi everyone, so today we'll be covering electrochemistry and redox. Basically, we have two different processes that can occur with electron transfer. One is that we can have electrons lost, which is oxidation, or we can have a gain of electrons, which is reduction. It's often useful to use this acronym here, oil rig. So oil is oxidation, is loss of electrons, and reduction is gain of electrons. So provided you can remember oil rig, you'll remember which process is which. So oxidation, the atom or the species loses electrons, and with reduction, the electrons are gained. So let's have a look at how this might come about. So for example, if we had copper 2 plus and it gains 2 electrons, it makes copper solid. This is an example of reduction. Also, if we had, say, 2 oxide ions and we form oxygen gas and release 2 electrons, that's an example of oxidation. So this brings us to oxidation numbers. Oxidation number is basically a measure of what oxidation state an element's going to be in at that time. It loosely indicates how many electrons are on that species at a given time, but it's not the same thing as formal charge. Okay, so there's just some general rules. So the oxidation number for an atom in its elemental form is 0. So if you have O2, each oxygen has an oxidation number of 0. If you have H2, each oxidation number has a number of 0. If you had iron metal, again, the iron metal would have iron with a 0 oxidation number. So the oxidation number of fluorine is always -1. The oxidation number of O, oxygen, is -2, except if it's paired with fluorine. Because fluorine's more electronegative, so it gets its way. It determines what oxidation number it's going to have, in this case -1, and so the less electronegative atoms have to have an oxidation number different than what they normally would. So generally with oxidation numbers, say you're in group 1 or 2, so like these cations down here, if you're in group 1 or 2, you'll have an oxidation number of +1 or +2 respectively. And same as if you're a halogen, so if you're in that group 17, normally if you form an ionic compound with those, they'll have a charge of -1. Well, generally the oxidation number is going to be -1, unless they're with a stronger, more electronegative atom. So oxygen's more electronegative than fluorine. So basically, the closer you are to fluorine, the more electronegative you are. If you have, say, a compound with, say, ICl, so iodine and chlorine mixed together, then the chlorine is more electronegative because it's higher in that group, and so it would have the -1 charge, and then the iodine would be forced to have a +1 charge. Okay, so basically, if the overall charge of a compound is 0, then the individual elements must add to give you 0. If there's a charge on the overall compound, which we'll do an example in a minute, then the overall oxidation numbers must add to give you that charge. Okay, so let's keep going here. So the oxidation number of hydrogen is +1 with non-metals, and -1 with metals. So if you had, say, sodium hydride, which is NaH, the hydrogen there is going to be -1. If you had something like HCl, which is hydrogen chloride gas, the hydrogen would be +1 and the chlorine would be -1. Okay, so that's basically all these rules. Again, the oxidation number of groups 1 and 2 is +1 and +2 respectively. So let's do an example. So what is the oxidation number of sulfur in S2O32-? So as I said before, the overall charge, if it's -2, means that all these species have to have the oxidation numbers add to -2. So in this, I know that oxygen is going to be -2 because it's the most electronegative atom, and so it gets the charge that it normally wants. So I can write this out as 2 lots of the sulfur plus 3 lots of the oxygen. Now the oxygen is normally going to be -2 for a oxidation number, must equal the overall charge, which is -2. So 2 of those sulfurs plus 3 lots of the -2 for the oxygens give you -2 here, and so then I can solve for the sulfur. So 2 lots of the sulfur, this here is going to be -6, so it goes over the other side for a +6. is going to equal plus 4. So each sulfur would equal plus 2. And you can check that out just to make sure it's fine. So if you put S2, if you have each of these charges, that there will give you 4. And then you'd have 3 lots of the minus 2, give you minus 6. So you'd have plus 4, minus 6, does indeed give you minus 2. Okay, so let's do another example. So if we have potassium phosphite here, each potassium we know is going to have a charge of plus 1 because it's in the group 1. The phosphorus we don't know. Okay, we do know the oxygen is going to be the minus 2 again, and the overall charge on that is 0. So this 3 plus the phosphorus minus 6 equals 0. So 3 minus 6 is minus 3. So phosphorus is going to equal plus 3. Okay, so phosphorus equals plus 3 for that. So most of this you should already be familiar with. So here's where it gets a little bit more difficult when we start looking at half reactions, then trying to balance more complicated oxidation reduction equations. So for half reactions, if we have the overall equation zinc solid plus 2 silver cations goes to zinc 2 plus 2 silver solids, we can break that up into half equations. We see that the zinc has lost 2 electrons here, and so to be zinc goes to zinc 2 plus 2 electrons. The silver has actually gained an electron to give silver solid. So just ignoring the stoichiometry there, we'd have silver plus an electron gives silver solid. So what about balancing in-depth redox equations? First of all, we have to know whether it's in an acidic environment or a basic environment. If it's not specified, you can just assume an acidic environment. So here we break it up into 2 different half equations. Okay, so the 2 different half equations would be the I minus going to I2 and the MnO4 minus going to MnO2. Okay, so I'll just look at these separately. So do the first one, it's not too hard. We have to first balance the stoichiometry. There's 2 iodines here, so there must be 2 here. Then we have to, there's no oxygens involved or anything, so this one's simply just a matter of balancing the charges. There's a 2 minus charge over here, so that means there must be 2 electrons here. Because there's a 2 minus, we need to have 2 electrons, so there's 2 minuses on either side. Okay. This one here is a bit more in depth. So first of all, we have to balance the stoichiometry. There's one manganese, there's another manganese. Okay, so that's 1 to 1 there. Ignore the oxygens for the time being when you're doing that. So now we have to balance the oxygens. So the way we do that is that we add water. So I add 2 waters, and that is going to result in now having 4 oxygens on the right hand side and 4 on the left. Okay, again, I ignore the charge at the moment. The charge is the last thing you do. So now I've introduced these hydrogens, and I have to balance the hydrogens. So I add protons to the other side. So there's a total of 4 hydrogens. So I'm going to have to add 4 H pluses to that side to balance that out. And so after that, then we have to look at the charges. So overall, there's 4 pluses and 1 minus here. That's a total of 3 pluses. Over here, there's no charges. So these 3 pluses have to be balanced out some way in order for me to have 0 overall charge, the same as what's on the right hand side. So I add 3 electrons. When I add the 3 electrons, that will give me a total of 0 charge here and 0 charge on the right hand side. Now I need to add these 2 equations together. And so before I can add them, I've got to have the same number of electrons. Okay, so here I'm going to multiply this equation by 3, and I'll multiply this equation by 2 in order for the condition that have the same number of electrons to be satisfied. Okay, so if I do that, I'll end up with 6I minus going to 3I2. Okay, for one equation, and for the other equation, I'm just going to ignore the electrons here because they're going to be cancelled off anyway. So for the bottom equation, it would be 8H plus 2MnO4 minus going to 2 MnO2 plus 4 waters. Okay, so I'm adding these two equations together, and so basically all I have to do is add everything on the left hand side of the arrows together. So it would be 6I minus plus 8H plus 2 MnO4 minus, so all the species that are on the left of the arrows. Then I'll put the arrow in, going to 3I2 plus 2 MnO2 plus 4H2O. Okay. So after all that, that's the overall balanced equation from here. Okay, so we still got our original species, the I minus, the MnO4, the I2, and the MnO2. But we've been able to introduce these other species that will have it balanced overall. Okay, so let's have a look at another one. This time it's going to be in a basic environment. So here again we split it up into the two half equations. So the NO2 minus and the NO3 minus is going to be one of those. And so to balance this one, the ends are the same. Okay, there's one N on either side. So now we have to look at the oxygens. So you know, it would be tempting just to add a half O2 here or something, but you can't do that with redox equations. So what we have to do is add a water here. Okay, and so I probably should have drawn this down a bit further. Okay, so I add a water there, and so now I'm going to have 1, 2, 3 oxygens, and there's 3 oxygens here. Then I've got to balance out the H pluses. Okay, so I'm going to have to add, sorry, I'm going to have to balance the hydrogen. So I'm going to have to add 2 H pluses to this side in order for that to balance. Okay, so now I've got to look at the charges. So overall, there's 2 pluses and 1 minus here. That's a total of a plus on the right hand side. On the left we have a minus. So in order to get rid of that plus and to have a minus, I'm going to add 2 electrons. Okay, so hopefully that makes sense. So you can never add positive charges other than the protons that you're adding here. But you can't just look at it and say, well, this is a plus over here, I should add 2 pluses over here. You can't do that. So you always have to add electrons to balance the charge finally. So so I have these 2 electrons and 2 H pluses. That gives a total of 0 there, plus the minus here. Gives me a -1 overall for the right hand side, which is the same as a -1 for the left hand side. So then I balance this other half equation, which will be the permanganate going to the Mn2 plus. Okay, so in this case I've got to add 4 waters to this side to balance out my oxygens. So that gives a total of 8 hydrogens here, and so I'm going to have to add 8 H pluses to that other side, so that there's 8 hydrogens on either side. Now, in order to finish it off, I have to balance the charges. So there's 8 pluses and 1 minus here, so it's a total of 7 plus on the left hand side. On the right hand side we just have the 2 plus. So I really need to add 5 electrons here, because the 5 electrons will add to the 7 pluses to give me just a 2 plus, and the same on the right hand side, I'll just have the 2 plus. Okay, so overall now I've got 5 electrons in this equation, and I've got 2 electrons here. The easiest way is to just multiply this one by 5 and this one here by 2 and then add them. Okay, so if I do that, I'm going to have 5H2O, okay, plus 5 NO2 minus goes to 5 NO3 minus plus 10 H plus 10 electrons. I can get rid of the electrons because there'll be 10 electrons on this other side too. Okay, so for the bottom equation, the second one, we have 16 H plus 2 MnO4 minus going to 2 Mn2 plus 8 waters. Okay, So I'm adding these two equations here. These two here. So when I add these equations, one thing I can do is look at, I'm going to have 5 waters on the left and 8 on the right. So really I can put in 3 waters on the right when it's time. I've also got 10 H pluses on the right and 16 on the left. Okay, so just look at everything on the left and everything on the right. So I really can just look at 6 H pluses on this side. So I hope that sort of makes sense. Maybe it's easier just to write the whole thing out. So maybe we'll do that. And just cancel them off later. So I'd have my 5 H2Os plus my 5 NO2 minuses plus 16 H plus 2 permanganates going to the 5 nitrates plus the 10 H pluses plus 2 Mn2 pluses plus 8 H2O. Okay, so just fit that in. So cleaning it up, like I said, there's really 3 H2Os overall. Okay, there's 10 H pluses here, so I might start with that. So 6 H plus is going to be left on the left hand side. There's still going to be 5 nitrites here, and 2 permanganates. So now when I go to this other side, I still have 5 nitrates. I don't have any H pluses anymore because I took into account with the 6 H's there, 6 H pluses. But I do have the 2 Mn2 plus, and I've got my 8 H2Os, but it's really 3 H2Os. Okay, so that would be the overall equation balanced in a basic environment, in an acidic environment. For a basic environment, what you're going to have to do is, because it's basic, we can't have our H pluses, so we have to get rid of those H pluses by adding 6 hydroxides. Okay, so if you add 6 hydroxides to this side, so I'll just do that here. You add 6 hydroxides to get rid of the H pluses. If I do that, this then will become six waters. So this will become 6 H2O plus my 5 NO2 minus plus 2 MnO4 minus going to 5 NO3 minus plus 2 Mn2 plus 3 H2O, okay, plus my 6 hydroxides. Okay, and so then overall I have these 6 hydroxides excuse me, because they're added to both sides, but overall I've also got 6 waters here and 3 waters there. So then to tidy this up, this would become my 3 H2Os plus my 5 NO2 minus plus 2 MnO4 minus going to 5 NO3 minus plus 2 Mn2 plus my 6 hydroxides. Okay, so that's that completed overall, and that's how we do that in a basic environment. Okay.